Welcome to my video on 7-1 and 7-2 word problems. Today we're going to be making exponential models for certain verbal problems and talking about the vocabulary words that go along with each. So for the do now, we'll start with the word problem that you probably could be able to figure out without using exponentials. It says each year the local park sponsors a free throw competition. Play starts with 128 participants. During each round, half of the players are eliminated. How many players remain after the 5 rounds? Okay, so let's think of it this way. In round 1, right, we have 128 members players, dwindling down to 64, okay? And we get that by dividing it in half, dividing it by 2. Okay, so at the end of round 1, we would have 64 players. In round 2, we take that same 64 and divide it by 2, and we get 32 players. In round 3, we get 16 players. In round 4, we get 8 players. And in the round 5, at the end of this round, we would have 4 players left, okay? So now let's think about what's really happening in this question, right? We are starting with a certain amount, and we are dividing by 2, but what we need to remember is that dividing by 2 is the same as multiplying by 1/2. So it's like we are multiplying 128 by 1/2, 64 by 1/2, 32 by 1/2, etc. Okay? Now, if you think of it this way, right? If we take this 128, it's almost like we are multiplying it by 1/2, 1, 2, 3, 4, 5 different times, right? Because, right, it's like we're taking it one step at a time. 64, then we get to 32, 16, 8, and then 4. Now, remember, when you multiply something to itself 5 times, it's the same as writing it 1/2 to the 5th power. So as you can see, this repetitive division, or repetitive multiplication really, eventually forms an exponential function when you are doing it over and over and over again, right? Yesterday we talked about equations of the form a times b to the x power. Well, this is the same thing. In this case, my 128 is a, and my 1/2 is b. And we are substituting 5 into x because that's the number of times it's happening. So let's take a look at this from, vocabulary standpoint. Same questions, okay? But now I'm applying vocabulary words to it. So the word that we want to think about first is, what is my initial value? Okay? What is the number that I am starting with? And that will always correspond to my A value. So in this question, we start with 128 participants. So as we saw with our first attempt, right, the initial value is 128. Now the question is this exponential growth or is this exponential decay? Remember, growth means that it is growing rapidly, right, from multiplication, and decay means that it's shrinking rapidly from repeated multiplication. So obviously, if we start at 128 and end at 4, okay, we really have exponential decay. And therefore, that decay factor is going to be what we are decreasing by, and it's going to correspond to our b value in our y equals a times b to the x format. So in this case, my b value, we said, was 1/2. And then there's the idea of the growth decay periods, or how many times this repeated multiplication is going to occur. In this question, we're talking about rounds. In other questions, we might be talking about minutes, years, days, hours, etc. Okay, so in this case, the decay and growth periods are going to correspond to my exponent, which in this case is going to be 5. Okay, so the exponential model that we are looking for, we actually already came up with, right? It's going to be y equals my 128 times 1/2 to the 5th power. Now, if you type that into your calculator, you should get the same 4. Now, obviously, this is a limited question, right? Because you could only have a minimum of 1 player left, right? But when we talk about other types of situations where we can get fractions of answers and decimals, etc., right? That exponent can be as small as 1 or as big as 1,000. Okay, and so instead of dividing by half 1,000 times, it's going to be much easier to use our exponential function equations. Okay. So the key word before we move on in this question was half. What I want you to remember is that when it says things are halving, right, or half of the players are eliminated, that means that my B value is going to be equal to 1/2. As we move forward, we're going to look at some other words that mean similar things but with different numbers. So here we have bacteria can multiply at an alarming rate when each bacteria splits into two new cells, thus doubling. If we start with only one bacteria, which can double every hour, how many bacteria will we have by the end of one day? Okay, so the key word in this question is going to be double. Okay, whenever we see the word double or doubling, right, that means that we are multiplying by 2. Okay, which means that my B value is going to be 2. Okay, and similarly, some other words you might hear is tripling, right? Means that my B value is equal to 3. So these are some key words that we need to be aware of. So this question is about doubling. Now, assuming we are forming an exponential model of the form y equals a times b to the x, okay, we need an initial value. We have our growth factor. We need an initial value. So it says we start with only one bacteria. So that means, not B, sorry. A is going to be equal to 1. Okay. How many bacteria will we have by the end of one day? Well, considering the fact that we are doubling every hour, our exponent x has to be in terms of hours, right? Our growth periods in this particular case is once per hour. Now, obviously, 1 day and 1 hour are two very different things. So we need to make sure that our exponents are adjusted to the unit that is expected in the question. So in this case, we have 1 day is equal to 24 hours. So into our exponent, we're going to actually put 24 instead of 1, right? Because we want to make sure the units are the same. So we type this in. So initial value is 1 times 2 to the 24th power. So now, 1 times 2 to the 24th power is equal to 16777,216. So that means at the end of one day, we're going to have 16,777,216 bacteria, assuming that we didn't wash our hands or didn't use any hand sanitizer. So what is the key takeaway from this question? Well, when things are growing exponentially, we have to make sure that we take preventative measures so that this doesn't happen, so that one bacteria doesn't turn into almost 17 million bacteria, right? So that's why we wash our hands and we use hand sanitizer. Okay. So now, not every question is going to have the word in it. Half, double, triple, a third, quartered, whatever the word is that means B directly will not always be the case. In many cases, they will tell you that growth is happening as a percentage, right? I'm growing by 20%. I'm growing at 30%, 5%. So when this happens, we have to make an adjustment to our B value, right? If we don't have the word directly, we're actually going to have to calculate this B value. Okay, so the calculation that's going to occur is this 1 plus, or if it's decay, 1 minus the percent as a decimal. Now, why is that the case? Well, if we are growing and we are multiplying by a number, if I multiply by just a decimal, let's say, right, 5%. If I multiply by just 0.05, it's going to decrease. Right? It's going to continuously get smaller. So I want you to think of it as this. At the end of every growth period, right, 100% of our items is still there. And we are increasing by 5%. Okay? Now, obviously, we can't do calculations with percentages. But if we turn both of those into its decimal format, we get the 1 plus 0.05 that we would get using this equation right here. Now, the same thing could happen if I'm decreasing by 5%, right? I have my 100%, but this time I'm taking away from it the 5%. Well, if we convert that into decimals, right, that's like I'm subtracting 0.05, okay? And so when we do make these calculations, just remember it can be a plus or it could be a minus, but it's not a plus or minus, if you get what I mean. Okay, so here's the model. Now we're moving into function notation. Remember, a of t is the same as y. It's just using function notation. That's what you get at the end of your calculations. A is still our initial amount, and t is still the number of time periods, except now you'll see more questions using t to represent time as opposed to x. Okay, and the only change that we see is that we are doing 1 plus r instead of having a b value, which we will calculate as we see to our left. Okay, so let's jump into this type of question. So consider a savings account with compounded yearly interest. Okay, so a savings account, preparing, right, to save some money. Now, the word compounded means that we are making interest. And now, if you don't know what interest means, interest is the money that you get from the bank for storing your money with them. Okay, now the compounded is when they are calculating the interest, and also tells you that the interest is being calculated on past interest that you've earned. So for example, if you put $100 into a bank account and you make a $1 in interest in the first year, in the next year, they're calculating the interest on the $101, which means technically you're making a little bit more money, okay? So that's the idea. Compounded yearly means you're making interest on top of interest, and it is occurring at the end of the year, or once a year. So we're going to start very basic here, where we have $100 that we are putting into the account. We're not taking anything out. We're not putting anything in. The bank is going to give us a 5% annual interest rate, which means that every year they're going to calculate 5% of what we have in our account and give us that amount of money. Can we come up with a function for this situation? Well, absolutely we can, right? Think about this. When we're making 5% annual interest, that means that we are multiplying it by the growth factor 1.05 every year. Okay, so it's going to be repeated multiplication. That is exponential. So looking at the equation that we just wrote down, y equals a times 1 plus r to the t, right? We have a is our initial amount, which is 100, plus 1 plus 0.05 to the t gives me 100 times 1.05 to the t, where t is going to be yearly. Now, what tells us yearly? Well, it tells me that it is compounded yearly, okay? And that the annual interest rate is yearly. So this is all words that mean years, okay? So now, the question I want to ask you, and I don't have it written down here, is, well, how much will we have in the account after 10 years, right? We have our model. How do we calculate it? Well, if we want to find out how much we'll have in 10 years, we simply just put the 10 in our exponent, right, and make our calculation. So 100 times to the 10. Okay, so that means at the end of 10 years, assuming I just left it in the bank, right, we have $162.89. So in 10 years, doing nothing, right, on your part, you've done nothing but not touch the money, you've been given $62.89. I know that's not a lot over 10 years, but if you think of this in terms of bigger investments and different percentages, eventually that'll add up. And again, you're not working for that money. You're simply just not touching the money. Okay, so when you're going to the bank and looking for savings accounts, right, you're looking for percentages of interest that you can make so that your money is making money while being there, not just sitting there and staying at the same $100 over the 10 years. Okay, now financial equations love to use exponentials, but so do medical questions as well. So we consider a patient who takes 100 milligrams of a medication. Once it's taken, the body filters out 15% of the medication from the bloodstream. Right? Think Advil. Every hour. What is the growth decay factor for this situation? And write an exponential model for this situation. I wrote that twice, so this is the same thing. Okay, so what is our growth decay? Well, first off, we have a decay question because remember, the body is filtering out 15%. Okay, so if the body is filtering out 15%, that means it's reducing. So we're going to take the 1 and subtract as a percentage 15%, leaving with my decay factor as 0.85. Okay, so that is my decay factor in this particular question. And the exponential model for it, remember y equals a times b to the x, right? A is my 100 of initial medication. B is the 0.85, and x is my time. And in this particular question, because it's filtering out every hour, my x has to be in terms of hours. So when we plug things in, we're going to be using hours. Now, the last type of equation that we're going to be looking at needs the introduction of a new number. And this number is Euler's number, right? I have that little mathematician guy there. And it's because it's was explored by somebody with a last name that starts with E, the letter that represents this number is going to be E. And we can find it on our calculator. Now, E is just like pi in that it is a irrational number, right? That was discovered by mathematicians to appear in many different types of problems. And it has a constant value. So I like to think of it as my Queen's kids, right? 2.718 is going to be my E value. And we can find that by pressing the second button and the E value above my division sign. And if you press that in your calculator and press enter, you will see 2.718 ... appear on our screen. Now remember, that's going to be a ... after it because it is an irrational number. And now what is this E value? Well, E appears many times in exponential functions, especially things having to do with nature and also things having to do with continuous change. So now, the reason that it does appear in nature is because when things change, it's not like a bank where at the end of the year they can give you your interest, right? Your tree doesn't grow and say, okay, it's December 31st, let me grow 2 inches, right? It changes continuously. So by looking at these different patterns in nature, they discovered this constant, 2.718, and we see that it occurs many times in exponential functions. Okay, now anything y equals e to the x has the same properties as all other exponential functions out there, right? We have an asymptote. We see, because it's 2.718, that it's growth, so it has the same general shape. It has the same y-intercept of 1, because even e to the first power is going to be equal to, e to the 0 power is going to be equal to 1. So it does have all those same properties, but we're going to be using it in questions that involve continuous change. Now, when Regents time comes, we'll look at some nature examples of this, but right now we're going to look at the financial applications. Okay, so the equation that we're going to be using is something called the continuously compounded interest equation, where interest is being compounded or calculated continuously. So instead of waiting for the end of the year to make a calculation of how much money you're going to get from the bank, it's doing it instantaneously, constant, over and over and over and over again. Now, using limits, which you'll see either in pre-calc or calculus, right, you'll be able to actually develop the number E, right, and figure it out and see where it came from. Now, for this class, you're just going to have to trust me that it exists and it is used in these types of problems, okay? And so what is the formula for this? Well, we have our function notation, a of t, right, which is the same as my y value. But now we've introduced a new vocabulary word, which is principal. Principal is the same as your initial value, except it is used primarily when you have financial questions. So when you start with an amount of money, it's called a principal. If you invest in a certain amount of money, it's called a principal. If you borrow a certain amount of money, that's called your principal. But it's the same as your initial value. So for the sake of the question, P is the same as your A value. Now, here's where things get a little bit different, right? Now, instead of having a growth factor in the question, we now have e as our base, okay? And we're going to be raising e to an exponent that includes our interest rate. Now, things to remember. The interest rate here is the percentage as a decimal, of course, because we can't calculate with percentages. But the other thing you need to remember is there is no +1 or no -1, right? Or 1 minus for these interest rate. You plug them in directly as you see them. So if it's 8%, you're plugging in 0.08, not 1.08. Okay, and t is the same. Now, most of these questions, because it's compounding continuously and you're making an annual rate, we're going to see time in years. We will talk when it gets closer to Regents time about what to do when the exponent changes a little bit. Okay, so we have our question. So Maria invests $6,154 in a savings account with a fixed annual interest rate of 8%, compounded continuously. What will the account balance be after 10 years? So there's a reason that compounded continuously is underlined. And that's the key words that you're going to be looking for when you use this formula, right? So we have A of t, or our y value, is equal to p times e to the rt. Okay, and that is exclusively used because we see compounded continuously. So now, what is my principal, or the initial amount? Right? Well, I am investing $6,154. Right? E is a constant. Now, R is my rate. In this case, my fixed annual interest rate. So we are now going to plug in 8% as a decimal into that exponent in place of R. And now T, because it's an annual interest rate, we're going to plug in 10 for 10 years. And this calculation will be able to give us the amount we have in our account after 10 years. So 6,154 times E. Remember, use second and then the division sign, or second and the ln button to get the exponent, times 10, and we get 13,695.9, and we round that to 8. So at the end of 10 years, this $6,154 turned into $13,695.98, which is pretty good. Okay, you're making a lot of money by just investing your money. So that's the idea behind investing, right? We don't want the $6,154 to just sit there in an account with no interest for 10 years. If we put it into account, that an interest-bearing account that will allow us to have our money make money, right? And that's the idea, is to get the money to make money. Okay. So now these are the homework problems for these particular sections. Things I want you to remember are the 3 types of problems we talked about. First, they're the problems with the words that tell me my growth factor. Things with half, double, right, triple, quartered, etc., right? And that tells me the B value directly within the question. Then we have the questions that talk about percentage growth, 20% growth, 30% growth, right? So when we see a percentage, our mind should be thinking, okay, well, what do we do with this percentage? Well, we take this and we're going to add for growth, and we are going to subtract it for decay as a decimal. All right, and so in this one, our B value is changed, but everything else is the same. And then we have that very special case where we see the words compounded continuously. Now, these questions will still have a percentage, but you will see these words compounded continuously to let you know that you're going to be using E in the question, and we're going to have to adjust our percentages accordingly. Okay? And that's it for this particular video.